Welcome back to the Deep Dive, the place where we take the densest research, the latest breakthroughs, and, the most mind-bending concepts, especially those hiding inside artificial intelligence, and turn them into knowledge that actually sticks.
Today, we are undertaking a really fundamental reassessment of how AI actually works. We're going right down to the most granular level,
You're moving past the big picture algorithm.
way past that.
Mhm.
We're going inside the individual unit of computation, the artificial neuron.
And what we found waiting for us inside is, well, it's not the tidy, simple structure we all assumed. For the longest time, the common theory, the intuitive sort of comforting default, was that the artificial brain was modular. Neat.
Yeah, we thought a single artificial neuron equaled one single interpretable feature.
A one-to-one relationship.
That was the dream, wasn't it? So beautiful, so clean. Researchers have a name for it. Monosemanticity.
Monosemanticity.
If you had a network that could recognize, say, a bicycle, the assumption was that you could point to neuron 53 and say, that's it. That one lights up only for bicycle handlebars.
And if that were true, we could just inspect every neuron and the entire mind of the AI would be legible, like reading a book.
You would be like having a perfectly labeled library.
Right.
But then came the reality check.
Right. This is thanks to that critical mechanistic interpretability research, primarily from groups like Anthropic, that really started surfacing between, 2022 and 2025.
Exactly. They essentially shone a bright light on that filing
I
cabinet.
realized everything was mislabeled.
Were stuffed in the wrong drawer entirely. They just flipped the script. They found that in large modern models, and this is especially true for the big language and vision models, this simple monosemantic view is almost never true.
Never.
Almost never. The vast majority of neurons are what they termed polysemantic,
Polysemantic.
multi-meaning.
So they aren't specialists dedicated to one feature.
Not at all. They're multi-tools. They're like jacks of all trades, juggling a whole stack of features that often seem completely random and unrelated.
And this messy reality is the core of our deep dive today.
Right. Our mission is to unpack the mechanism that causes this. And the answer really is found in a concept called superposition.
Superposition.
It's the network's incredibly efficient, but also highly complex compression strategy. We'll show you why the AI is basically forced to hide information.
And then we'll get into the cutting-edge mathematical tools from these toy models to things called sparse autoencoders that researchers are now using to find the true features.
Which aren't neurons at all. They exist as hidden directional codes in a massive high-dimensional space.
This is truly about building that sophisticated stethoscope for AI.
It is. It's about learning to listen to the network's true underlying signals. And our knowledge today is built from that recent research focused heavily on mechanistic interpretability, the quest to finally understand how these intelligent systems actually process information.
Okay, let's start with that puzzle. The neuron that wears many hats.
Yeah, let's drill down into that original misconception, monosemanticity, because it's just so intuitive. It's what we want to be true.
Of course. In that tidy, expected world, interpretation is. It's just a direct, simple lookup table.
A lookup table. Perfect analogy. If you're a network trying to detect faces, you expect neuron 100 to be the left eyebrow detector.
Right. It activates only when that one specific feature is present. It's a dedicated, reliable specialist. The moment it lights up, you know exactly what the network just saw. No ambiguity.
And that idea was so compelling because for a while it seemed plausible. I mean, it's how humans tend to build systems. We like modularity, so we projected that onto AI.
But once researchers had the tools to actually inspect the activation patterns of these large, powerful networks,
They consistently found the tangle. Polysemanticity is the rule, not the exception.
and this is where the mystery really kicks in, because the polysemantic neuron isn't just a little messy, it's bizarrely mixed. It fires from multiple features that, on the surface, have zero connection to each other.
Zero. And the initial reaction by researchers was, I think, genuine shock. We're not talking about a neuron that fires for, like, dog ear and wolf ear.
Because that would make sense. They're related concepts.
Exactly. We are talking about situations that just defy human logic. I mean, think about the examples found in the research. A single neuron might fire for a cat image, and a car image.
Okay, a cat and a car. I'm trying to find a link. Curves, headlights and eyes. I mean, you can stretch it, but it feels like a stretch.
It is.
Mhm.
And it gets more abstract. In a language model, a single neuron might code for the concept of an apple and the concept of a mountain.
An apple and a mountain. Okay, that one really sticks out. Let me try. I have to try and find a connection. If it's a visual feature, maybe it relates to texture. No, mountains are rocky, apples are smooth. Okay, what about scale? No, apples are small, mountains are huge.
Yeah.
Is it possible they both relate to being natural objects in contrast to, say, a keyboard?
And that is a perfectly logical, perfectly human attempt to find a shared semantic link.
But it's wrong.
But that's the polysemantic puzzle. The research strongly suggests those features, apple and mountain, are not fundamentally linked by a common semantic concept or even a shared visual structure. The network is using them for tasks that are just statistically independent.
So it's not a conceptual link. It's a convenience thing.
It's computational convenience. The network doesn't think apple and mountain are both things that exist outside. It thinks, I need to represent feature A, apple, and feature B, mountain, and they'd appear rarely enough in my training data that I can safely cram them into the same physical space without causing a total disaster.
So they're jammed together because of an architectural necessity, not a conceptual one.
Precisely. And we see this ambiguity everywhere. Another one that's often cited is a neuron that fires for smiley faces and mathematical symbols.
It's even weirder.
It is. And when we, the external observer, see that neuron activate, we have no idea if the AI is processing an equation or a piece of internet shorthand.
The moment researchers realized this was widespread, the whole foundation of interpretation just cracked. The neuron, which we assumed was the fundamental readable unit.
It's now fundamentally ambiguous. It is the definition of a black box, but at the micro level.
So that forced a paradigm shift.
It had to. We had to abandon the search for the specialist neuron. If the features are packed together inside the neurons, then the real interpretable units of computation must be hidden beneath the activation patterns.
And that requires a totally new mathematical method of extraction.
Right. And this necessity, this whole idea of computational economy, is explained by superposition.
Okay, let's unpack superposition. This is the key concept that makes sense of the polysemantic mess. We've established it's a solution to a space constraint problem.
A severe space constraint problem.
The network is trying to store far more features than it has dedicated physical units, the neurons.
That's absolutely right. And just think about the scale for a second. A large language model might have, I don't know, a few 100,000 neurons in a single hidden layer. But the real world, the language, the concepts, the patterns, the styles it needs to represent, that requires it to learn millions, maybe even billions, of distinct latent features.
So if the model has n physical neurons, but the training data demands it represent, say, 10n features, it faces this profound compression challenge. You can't just throw the extra features away.
No, you can't. The model needs them to perform accurately. So superposition is how it cheats.
It cheats. I like that.
It means features don't live in a single dedicated node. Instead, they are encoded as overlapping patterns of activity across a whole collection of neurons. Features share space by existing as mixtures within the available computational units.
Okay, the light switch and color analogy you mentioned earlier is critical here. Let's spend a moment on it just to really solidify this concept for everyone.
Great idea. So imagine, if you will, being forced to design a lighting system with only 10 physical light switches. Those are your 10 available neurons.
Okay, 10 switches.
But you have to be able to create 100 distinct colors. Those are your 100 features. Now, in the monosemantic world, the simple world...
You could only make 10 colors, one switch, one color? Done.
Exactly. But in the world of superposition, you wire your system differently. You wire it so that switch 1 contributes a bit of red, switch 2 contributes a bit of blue, switch 3 a bit of yellow, and so on.
They're all ingredients.
They're ingredients. Then, to create color 42, maybe you turn on switch 1, switch 5, and switch 9, all to varying degrees.
And to make a different color, color 77.
You turn on, say, switch 1, switch 3, and switch 8. And notice...
Switch 1 is involved in both.
Right. That neuron is polysemantic. It participates in multiple distinct features. You've used overlapping codes to achieve massive representational efficiency.
Okay, this leads to my big question. If the network is constantly mixing these features, like you said, mixing sound waves on the same radio channel, doesn't that cause massive interference?
Yes.
I mean, if the Apple code and the Mountain code share a neuron and I try to activate the Apple concept, doesn't the Mountain concept start interfering and just muddying the whole calculation?
It absolutely does cause interference, and this is where the efficiency calculation gets really nuanced. The cost of compression is interference, but the network is highly specialized to clean up that mess.
The ability to manage this interference is why it all works.
It's the only reason it works.
So how does it manage it? This feels like a crucial technical point that's often just skipped in high-level summaries. How does the network filter out the interference?
The secret lies in the nonlinear activation functions, specifically something called ReLU or its variants like JLU, which are applied right after the weighted sum in the neuron.
ReLU, rectified linear unit.
That's the one. And you can think of these functions as being highly effective cleanup crews.
Okay, explain how ReLU works in this context.
So standard computation in a network involves matrices and vectors. When features overlap, the signal for the feature you want might be strongly positive, but the interference signal from the feature you don't want might be weakly negative.
It's pulling in the wrong direction.
Just slightly, yeah. ReLU works by a very simple rule. It sets all negative inputs to 0. It just says, if the combined signal is less than 0, I discard it completely.
So if the apple feature vector is pointing strongly in one direction and the mountain feature is interfering by trying to pull the signal slightly in the negative direction, ReLU essentially just snips off that negative interference.
Exactly. It enforces a critical form of sparsity after the initial compression. It filters out the noise and only allows the strong, positive, intended signal to pass through to the next layer.
Wow.
This mechanism is key to why networks can handle these highly compressed, overlapping codes. The ReLU operation is constantly clearing the channel, filtering out the crosstalk caused by superposition.
So the compression strategy is only viable because the subsequent layers, powered by ReLU, are designed to aggressively discard irrelevant negative noise. That's a beautiful system.
It is. And this compression is most effective under one key condition.
Which is?
When the features are sparse. This is the mathematical reason the network is willing to accept the risk of all this overlap.
Let's define sparse clearly again. It just means rare, right? Infrequently encountered features?
Correct. The network is essentially taking a massive statistical gamble. It knows it needs to learn the apple feature and the mountain feature, but they are relatively rare in the corpus, and, crucially, they are statistically unlikely to be needed at the exact same moment in time.
It's betting that the risk of feature A and feature B both lighting up at once and causing catastrophic interference is just very, very low.
Exactly. If you have 10,000 rare features and you only have 1,000 neurons, you can maybe pack 10 features per neuron, just assuming that only 1 or 2 of those features will ever be relevant in any single input.
And if the features were dense, if they were required all the time?
Superposition would fail instantly. It would be constant, unavoidable interference, a total mess. But because most features are scarce, the network benefits from this massive efficiency gain, compressing information far beyond what any simple, linear, non-overlapping system could ever manage.
But I have to ask the obvious question again. Why not just build a bigger network and avoid this mess? If interference is the cost, surely the computational overhead of constantly cleaning up the noise with ReLU must be almost as expensive as just having more neurons dedicated to clean features.
That's a profoundly important question, and it really speaks to the training dynamics and, the physical constraints of deployment. Firstly, bigger networks mean vastly more weights.
More memory.
Far greater memory requirements. Superposition minimizes the weight count required to store those millions of features.
So it's a memory constraint more than a raw speed constraint.
Primarily, yes. Furthermore, you have to think about how the network is trained. It's using gradient descent, and it's always just finding the path of least resistance to minimize its loss function.
The path to getting the right answer.
Right. And if the network can achieve high performance by finding an efficient compressed sensing trick, which is what superposition is, it will naturally adopt it, because there is no explicit penalty in the loss function for polysemanticity.
The network doesn't inherently care if we can interpret its neurons.
It doesn't care at all. It only cares about successfully predicting the next token or classifying the image. Superposition is simply the most efficient path it found to meet its performance goals under its architectural constraints.
So the messy polysemantic neuron isn't an error, it's a signature.
It's the signature of an extremely optimized, efficient computational machine that prioritizes compression over human legibility.
Okay, so that's the paradigm shift. The individual neuron is no longer the fundamental unit of meaning.
Right. Which forces us to redefine what a feature even is in this world of compressed codes. The reality of superposition has pushed researchers into a much more geometric way of thinking.
Which means features are not single nodes, they exist as directions. or axes in this high-dimensional activation space. That's a conceptual leap. We need to make sure we really solidify that for the listener.
Okay, let's start with the basics of that space.
Yeah.
Every time the AI processes an input, a sentence, an image, whatever, it generates what's called an activation vector.
A vector?
Yeah. If the network layer has, say, 10,000 neurons, that activation vector is a single point in a 10,000 dimensional space. And this vector describes the complete state of the network at that exact moment.
So that state, that single point in this massive room, is determined by the output value of all 10,000 neurons simultaneously.
Correct. Now let's go back to the stage dimmer analogy, but let's push it into this geometric realm.
Okay, so we're backstage again, and we have 100 dimmers, or 100 neurons. The exact setting of all 100 dimmers creates the specific light scene on stage.
And that light scene is our point in the 100-dimensional activation space. Now, consider the feature. Let's say the subtle upward curve of a dog's tail. In the old monosemantic world, that feature would be represented by...
Just turning on dimmer 17. Simple.
Simple, but we know that's not right. So in the superposition world, that feature, the dog's tail, is a recipe.
A recipe.
It's achieved by turning dimmer 5 up 70%, dimmer 12 down 10%, dimmer 33 up 40%, and leaving all the rest off.
It's a combination.
That specific recipe, that combination of simultaneous activity across many dimmers, defines a direction, an axis in the space of all possible dimmer settings.
So when the network sees that dogtail, the activation vector, that point in the room, it shifts along that specific axis.
That axis is the feature.
And if two features, like apple and mountain, are packed into the same neuron,
It simply means their directional codes, their recipes, both require turning on that one shared dimmer. But they achieve their unique directions by turning on other dimmers in totally different combinations.
so their overall direction, their vector, is still unique, even though they share overlapping components.
Exactly. They might be very close vectors in that high-dimensional room, but they are not identical.
This view is incredibly powerful. It gives us a clear objective for interpretability. Stop hunting for the nodes and start hunting for these geometric axes.
And this geometric view is really reinforced by the formal definition that researchers have started to adopt for what a true feature is.
What's the definition?
A feature is what a larger, more capacious network would assign to an individual neuron if it could.
Whoa, okay. That is such a key definition. Say that again.
A feature is what a larger, more capacious network would assign to an individual neuron if it could.
It confirms that our current messy network is just doing its best to mimic an ideal, clean network. It's running a noisy simulation of perfect modularity.
It recognizes that the fundamental unit should be monosemantic, but the space constraint forces those monosemantic features to compress into these directional overlapping codes.
So the challenge becomes one of mathematical decomposition.
Right. We have to look across the activity of many neurons at once, using linear algebra to find the hidden directional code that represents these true underlying concepts.
But we can't just start by dissecting a billion parameter model. That's impossible. We have to start small.
We have to start small, which brings us to the research strategy.
Big insights from tiny models.
Exactly. The scale of the problem is just. It's overwhelming. Analyzing a large language model is like trying to navigate a maze with a million dimensions. The linear algebra alone is computationally prohibitive.
So researchers had to revert to something much simpler to test their theories.
They adopted the toy model approach, which is indispensable in this field. And these aren't trivial experiments. They are the controlled physics laboratories of AI.
The particle accelerators.
When we can't observe the structure of the universe directly, we build particle accelerators. Toy models are our accelerators.
And they are tiny neural networks, right? Maybe just 2 layers with a handful of hidden neurons.
Sometimes just that. They're trained on very simple synthetic tasks.
Synthetic tasks.
Yeah, they're intentionally minimal. For example, a researcher might train a 2-layer net with only 10 hidden neurons and tell it to learn 50 synthetic features. The researcher knows exactly what features should be learned, and they can precisely control variables like the sparsity of those features.
So they can run true cause and effect experiments.
That's the whole point.
Yeah.
And the findings from these controlled environments were essential. They gave us the validation that superposition is a deliberate, mathematically driven strategy, not some random accident.
So what was the first key insight?
The first key insight came from observing phase transitions.
Phase transitions. That sounds incredibly technical. How does a network undergo a phase transition like water turning to ice?
It's a surprisingly good analogy. In a controlled experiment, researchers can train the network on a set of features and then gradually increase the number of features it must learn. Or they can decrease the sparsity, making the features more common.
Okay, so they're turning up the pressure.
They're turning up the pressure. For a while, the network handles the features neatly. It dedicates one neuron per feature. It's monosemantic, it's linear, but there's a sharp tipping point.
The moment the demand for features outstrips the physical space available.
Precisely. Once the ratio of features to neurons hits a certain critical threshold, maybe when the feature count is 3 times the neuron count, the network doesn't just gradually get worse. It undergoes an abrupt, radical shift in strategy.
It flips a switch?
It flicks a switch. It sharply and suddenly abandons the monosemantic strategy and adopts superposition, packing multiple features onto single neurons, almost instantly.
That suggests a powerful computational instinct at work. It's like the network's optimal survival strategy under duress.
It is. It's this nonlinear behavior that demonstrates superposition is the mathematically preferred mode of operation when sparsity and space constraints align just right.
What else did the toy model show?
They reveal that even the most optimized networks are mixed networks.
Mixed networks, meaning they contain both specialists and multi-tools.
Yes. The network allocates its limited space strategically. The few, highly important, very frequent features will often be assigned their own dedicated monosemantic neurons. Those are the specialists.
Of the rest.
But the vast majority of the remaining neurons are used for the polysemantic compression of all the rare features. This blend makes the whole system extremely flexible and efficient,
So it minimizes the risk of interference for the most critical computations.
while maximizing storage for all the rare long-tail knowledge. It's a brilliant trade-off.
Okay, now let's talk about the most fascinating finding, the one that truly suggests this hidden order. The structured pattern.
This is where the linear algebra confirms the elegance of the AI solution. When features are compressed through superposition, they don't just overlap randomly in a messy pile.
They don't.
No. The network mathematically organizes their directional vectors into incredibly neat geometric configurations in that high-dimensional space.
To minimize interference.
Exactly. It's all about minimizing interference.
Give us an example of these shapes. What do they look like?
Well, they often form things like antipodal pairs.
Antipodal pairs.
Yeah, imagine a sphere. Two features that form an antipodal pair are represented by vectors pointing in exactly opposite directions. One points north, the other points south.
Okay, why is that useful?
Think about it. If feature A and feature B are rare and opposite, activating feature A involves pushing the weights in one direction, and feature B involves pushing them in the exact opposite direction.
So if I accidentally try to activate feature A when I only needed feature B, the strong negative pull from feature A's vector will essentially be
Zeroed out by the real U function. It cleans the noise almost perfectly.
it minimizes the crosstalk. That's clever.
It's very clever. They also find structures like triangles or even tetrahedral arrangements when 4 features are packed together.
A tetrahedron, like a pyramid with a triangular base.
Right. And the tetrahedron is the optimal geometric configuration for 4 points in space to maintain the maximum possible angular separation from each other.
So the network is literally using geometry to minimize the risk of interference. It's a spatial separation trick, hidden in the mathematics of its structure.
It's proof. It's proof that the chaos we observe at the neuron level, that cat-car neuron, is just the surface manifestation of a profound, hidden mathematical order, an order designed for ultimate efficiency and anti-interference.
And these findings from toy models give researchers the confidence.
The necessary confidence that the same underlying principles govern the complexity we see in massive real-world systems, whether they're processing language, vision, or complex internal concepts. We know the structure is there. We just need the tools to find it.
So the features are directional codes, geometrically arranged to minimize interference. The final, Herculean task is building the decoder ring needed to extract those hidden vectors from a system with millions of dimensions.
And for this, we rely entirely on mathematics. Linear algebra provides the vocabulary. We're talking about vectors, basis, projection, and critically, orthogonality.
Let's simplify orthogonality. We said it means perpendicularity. Why is that the key to feature separation?
Because if two feature vectors are truly orthogonal, if they're perfectly perpendicular in space, they are mathematically independent. They have zero overlap and zero crosstalk.
So if feature A and feature B were orthogonal, activating A would have absolutely no effect on B.
None. That is the ideal, clean, monosemantic world.
But because superposition forces features to overlap, they are not orthogonal.
They are forced to be non-orthogonal. Researchers sometimes call them almost orthogonal. They're slightly angled toward each other, which causes that necessary crosstalk we discussed.
So the job of the interpretability tools
Is to use math to find a new set of directional vectors, a new clean basis that is as close to orthogonal as possible while still accurately explaining the messy polysemantic activity of the network.
This sounds like a computational nightmare. What is the practical, powerful tool that can actually perform this massive decomposition?
That would be the sparse autoencoder, or SAE.
The SAE.
It's a dedicated, separate neural network that is trained specifically to analyze and decompose the activation patterns of the main AI model.
So the SAE is essentially a smaller AI that specializes in listening to the high-dimensional internal conversation of the big AI. Walk us through its mechanism.
Okay, an autoencoder has two parts, an encoder and a decoder. The encoder takes the high-dimensional, messy activation vector from the main model and tries to compress it into a much smaller, dense intermediate layer.
It squishes it down.
It squishes it down. Then the decoder takes that compressed representation and tries to reconstruct the original messy vector from it.
And if the autoencoder can accurately reconstruct the original input, it means it has successfully learned a way to summarize the main network's internal state.
Exactly. But here's the key. That crucial word, sparse. We don't want a standard compression. We introduce a severe penalty during the SAE's training process.
A penalty for what?
We tell it, you must represent this information, but you are not allowed to activate too many of your internal components simultaneously. This is the sparsity enforcement.
Ah, this is the genius move. The main network uses messy, overlapping codes polysemanticity because it has no penalty against it. But the smaller SAE is forced to find a clean, non-overlapping way to represent the exact same information.
It's compelled to find the simplest, most minimalist representation possible. When the SAE's internal components activate, they must activate alone. And this forces the SAE to learn a compact dictionary of basis vectors.
And what do these dictionary items represent?
Each basis vector learned by the SAE, because it is forced to be sparse, aligns almost perfectly with one of the hidden, underlying monosemantic features we've been looking for.
The true feature directions.
The true feature directions. The sparse autoencoder is essentially decomposing the jumbled polysemantic neuron activity of the main model and transforming it back into a monosemantic feature dictionary.
That's a profound reversal. It takes the network's efficient compression trick and mathematically undoes it, giving us back the legibility we lost to superposition.
It's like putting the overlapping radio signal through a perfect filter and isolating every single song, loud and clear.
The power seems undeniable. Has this been used successfully?
Oh, yes. Research published in recent papers, particularly on the application of SAEs to language models, has shown this method can successfully uncover thousands of interpretable features that were previously just hopelessly tangled in the polysemantic neurons.
Like what kind of features?
Things relating to specific grammatical roles, specific sentiment markers, or specific factual concepts like, the names of U.S. cities.
However, we must address the cost. This doesn't sound easy to implement.
It is not. While the theory is clean, the practice is very challenging. Sparse autoencoders require extensive computational resources.
How extensive?
Training them on just one layer of a giant model can take days or even weeks on a cluster of GPUs.
What?
And on top of that, the hyperparameter tuning, especially determining the precise level of sparsity required, is a complex art. If the SAE is too sparse, it misses features. If it's not sparse enough, it fails to separate them cleanly.
And even once we have the isolated vector directions, the interpretation still falls back on human researchers, right?
It does. It falls back on them to look at the activation patterns and say, this specific vector seems to represent the concept of historical date references. The SAE provides the clean dictionary, but human insight is still required to read and understand the semantics of that dictionary.
It's a powerful lens, but we still need the scientists behind the microscope.
Exactly.
Okay, so we've established the new reality. AI features are compressed, directional codes hidden via superposition, and we have the mathematical tools to start untangling them. But this field of mechanistic interpretability is still very young. It must face immense open challenges.
Immense is the right word.
Let's revisit the core question. Why does the network use superposition at all? If we were to design an AI from scratch, and we knew the cost was this hidden complexity, couldn't we force it toward modularity? Maybe by adding a penalty for overlapping features during training?
That is a very active area of research. We understand the physical and statistical reasons, efficiency, feature sparsity, but many researchers are now experimenting with imposing explicit sparsity constraints, not just on the activations, but on the weights during the initial training phase.
And what's the challenge there?
The challenge is balancing interpretability against performance. It's highly likely that the superposition trick grants a certain subtle performance edge that a strictly modular system might lack. It's a compressed sensing trick, and sometimes those tricks are just mathematically superior.
Then there is the monumental challenge of scale. We're talking about models with hundreds of billions of parameters. Applying SAEs to analyze every layer of every component, from the attention heads to the MLP layers, that has to be overwhelming.
It is a massive computational bottleneck. Scaling up this decomposition process is technically framed as a dictionary learning problem over incredibly high-dimensional data.
We need faster tools.
We need faster, more automated methods for finding these feature directions. If it takes a supercomputer days to analyze one layer of one model, we can't keep up with the pace of AI development. We need algorithms that can reliably find the feature vectors and flag the most important ones without constant human oversight.
And once we find the packed features, the next layer of complexity kicks in. How does the AI actually calculate with information that is packed and overlapping?
This is the real frontier, deciphering computation under superposition. It's not just about finding the features, it's about mapping the circuits. When feature A and feature B are non-orthogonal, how do subsequent layers mathematically ensure they only use feature A's code and completely ignore B's interference?
Where are we looking for answers to that?
This is leading researchers to look beyond traditional AI analysis and draw on ideas from neuroscience and potentially concepts like vector symbolic architectures, where calculations are inherently performed using high-dimensional vectors.
The final challenge, as always, is generalizability. We've seen great structure in vision models in these small toy examples, but does the beautiful geometric order, the antipodal pairs, the tetrahedrons, does that hold true in the most complex, abstract layers of massive language models?
That mapping is ongoing. We need confirmation that the hidden structure found in the activations of smaller tasks reliably carries over to, say, the factual recall or creative text generation circuits of LLMs. We are only in the early stages of creating these comprehensive feature dictionaries for the largest systems.
So bringing it all back home, why should our listener, who might be preparing for a meeting or just aiming to be generally well-informed, care about this deep dive into compressed codes and polysemantic neurons?
Because understanding this compression is the essential key to building transparent and reliable AI. The black box isn't blank because it's mystical. It's blank because it's compressed.
And if we know the network is running a compressed sensing trick,
We can finally move past vague theories about its behavior. We can rigorously identify hidden failure modes. We can debug potential biases by isolating the specific compressed feature vectors responsible for them.
here crucially, we can find the hidden features responsible for those miraculous emergent abilities that surprise even the creators themselves.
This knowledge shifts our perspective completely. We're moving from guessing what the AI mind is thinking to actually having the mechanistic tools to read its fundamental language. We now know what to listen for, the directional signals buried in the noisy polysemantic activation space. That knowledge doesn't just stick, it fundamentally changes how you perceive the entire field of AI.
Today, we journeyed from the assumption of the tidy specialist neuron to the reality of the polysemantic multi-tool neuron, elegantly explained by the compression strategy of superposition.
We saw the profound insight gained from running small, controlled physics experiments in toy models.
And we discovered the promise of powerful mathematical decomposition tools like sparse autoencoders, which act as our decoder ring.
And here's the final thought for you to take away and mull over. The greatest discovery in the interpretability of artificial intelligence is that the seemingly chaotic complexity is actually a profound form of hidden order. Much like physicists studying the subatomic realm, AI scientists are proving that the most efficient way for our systems to function is to rely on underlying mathematical principles and compressed codes.
So the complexity isn't a bug.
The incredible efficiency of modern AI isn't a bug or a random occurrence. It's a meticulously structured, high-dimensional compressed sensing trick. And we are only just now learning how to fully decode the elegance of the artificial mind.